Imagine being asked to design a 20-meter beam in reinforced concrete with no intermediate column. And the client and the architect doesn't want to use steel because of several reasons, the cost and other things. And this has to work. In this video, I'll be showing you the engineering logic, not just the software procedure, but the engineering logic behind every decision on how to design a 20-meter beam using a real-life project which I just designed here. My name is Engineer Justice Nwaka, and in this video, you will learn the real concept or engineering concept to design a long span beam, just like this 20-meter beam you are seeing here on my screen. And also, you will also learn how to make the right engineering judgments on any kind of design in terms of long span beam or a short span beam. And also, following this video on this concept, which is a long span beam, I'll also show you the right decision for a long span beam of this, either to use a column or a shear wall at the ends of the beam. As you can see that this beam here, there are two beams of 20.03 meters that I have here. And it's a very long span beam without any column at the center or intermediate. And you can see that I used a wall at the ends of this, which you will know by the end of this video why you must not use a column when you are designing for a long span beam. Instead, it is best to use a shear wall. Also in this video, I'll also show you the connection on what to do, how the connection or the support between the long span beam and the reinforced concrete wall which you're using as the support are meant to be connected. Because if there is no enough anchorage length between this column and the reinforced concrete wall, then there will have to be a split between these joints. I'll also show you the principle on what to do there. So these are the things you will be learning by the end of this video. So stick around and then let us begin. Now, before we start, if you're new on Ekidel, consider subscribing. And if you're an old subscriber and you want to get an in-depth knowledge about most of our advanced videos, consider joining the Ekidel membership. Because there are some videos here that are only for members, and those are very, very critical videos that we explained enough there because we have much time to explain there. Okay, that is fine. So to now dive into this now, let me now walk you back to, now this building has already been designed for, which you can see the analysis here, and this is a real life design, which you can see the structural detailing here. So you can see the detailing of the foundation, which you can see here, foundation layout. And then for the first floor, which we have directly here, this is the first floor, which you can see here. This is the first floor of the beams and column layout. And then all other ones, this is the full detailing that we have here. But let us dive in back to what we have today, which is for the structural design for the long span beam of 20 meters. So now we now come here and then open up this place now. Now on this place now, we then dive in back to the plan view of where this 20-meter beam is. So we go to the plan view now. This is the foundation layout for the foundation design. So that is basically on the story 2. Yes, story 2. That's where the 20-meter beam is. So this is the plan view or the plan layout of this building you just saw, the 3D model and the detailing you just saw. So it has basically an expansion joint, which you can see there because of the shape of the building and the span of the building. Now you can now see this is place where we have the 20.0 meter and 20.03 meter beam, which you can see here, 20,300 meters beam. So in that course, you can see now, so basically this happened because the client or the architect doesn't want to have any intermediate column. It was first designed to have a column because it is a hall. This whole area is to be like a conference hall, which you can see here, an open area, and it's a double volume. As it spans through, the height spans through from the ground floor down to the next floor upper. So it's actually about 8 meters high. Yeah, 8.4 meters high, which you can see here, 8.4 meters high. Yeah, from the lower ground level. So the architect and client doesn't want intermediate columns. And okay, so let's use a steel, which they said no, that they want it to be concrete, understand, which is still workable when I looked at it, even if the span is 20 meters. Okay, that is fine. So in that course now, I now modeled the 20-meter beam. Now, what is the concept of modeling the 20-meter beam? Because right now, because of the span, what should come to your mind? What will be my section? As you can see, in this case, I used we are open here now. You can see that I used the beam section size to be what, width 600 and the depth 2.4 meters. If I open up this property now to look at for that, come here and then open up the property here, and that shows up just here now. Now on this here now, you can see that the width of my beam is 600 and the depth of my beam is 2.4 meters. Okay, and I didn't release the moment. I have to make to be what fixed, because I needed the joint to be very, very rigid and not flexible. Okay, that is fine. So in that case, I didn't apply hinge or pin end at the ends of the beams. Okay, that is fine. So this is the depth. Now, based on this depth, how do you assume your depth, or do you just choose any depth you want? No, you don't just choose any depth that you want. First, you have to follow the rule of thumb first when it comes to beam depth. Okay, that is fine. And what's the rule of thumb for the beam depth? Okay, let me just close this other one here first. So the rule of thumb for the beam depth is very simple. Span, that's L over what 12 or L over what 15. Okay, that gives you a guide on how to pick your how to assume your depth of your beam. Now, note that this thumb rule is only giving you this depth based on the span and not based on the load. Okay, so if I now do L over 12 or L over 12 or L over 15, that gives me what? That gives me 20, 0, 300. That's the span of the beam, which is L, all over divided by 12. That gives me what? That gives me almost 1.7 meters depth of beam. Okay, if I do L over 15, that is 2300. Okay, all over 15. This is the thumb rule. That gives me almost 1.4. So that means that my depth of beam, basically based on the thumb rule, is meant to be assumed 1.4 to 1.7 approximately. Okay, that is fine. Now these values are based on what? Based on the thumb rule. Okay, without the loading. Now, if you notice, now we have a slab here. With the slab at the top of the slab here is to be used for like a restaurant. Okay, a restaurant. So by the time you factor all the loads of this area of the slab and everything, that is why my depth of beam changed from 1.7, which was the assumed depth that's meant to be, to 2.4 meters. Now, note that depth of beam of L over 12 or L over this thing is not your actual depth. That's only a thumb rule. But what governs is after your design. What is the depth that now satisfies the design? So in this case, 2.4 depth satisfy the design. Now, why did I use 600 as my width of my beam? If you open here, you can see I use 600 here as my beam width. Now, I use this as my beam width because knowing that this is a long span beam, all right, the numbers of the reinforcement and to expect will be much. They won't be let me say 40, 25 or 40, 16 order. I'll be expecting something like 6 to 7 to even 10 to 11 T25. So in that case, I need enough width to have enough width so that those bars will not be clustered together like this. They won't be clustered. They should be spaced. Else, if they are clustered, concrete cannot pass through when they are casting it. So at that point, if concrete cannot pass through when they are casting it, after casting, under the beam will be left with void. And when there is void, there will be what? Air. And when there is air, there is what? Oxygen. And when there is oxygen, what happens to do what? It will cause rusting to the reinforcement over time. It can take 5 years, 10 years, but it will rust because there is what? Oxygen present inside the beam. Okay, because of the void. So just to avoid that issue, I have to do what? Give enough width of the beam. Okay, that is fine. Then in that course now, let's now proceed to, because I've already done the structural analysis already, which I believe you already know how to model if you've been with us on the channel. So the same way you model your building, the same way just model using the same principle. Now if you now move to the beam design for this, if I open this one now and then open the system design for this, you will then see first of all, we go to the shear force and the moment value, which we to display just now. Now, if you now look at now, this is the final rebar arrangement that we used for the real life construction of it. And perfect, before we look at for this, let us look at for the shear force and BM diagram. So we open here now, and then you will see the massive shear force over 6,000 kilonewton-meter for the bending moment diagram. Sorry, bending moment value. Now this is the shear force here at the top here, which takes care of the links. This shear force is used to take care of what the links. Tells you the links you're going to provide, so that there won't be any bursts of the beam. Else, if the ties, if the links or the stirrups are not sufficient, it will burst. Understand? So this shear force takes care of the gives you for the links. Now this is the BM diagram, as you can see that. Now since we didn't, now you can see the moment at the support at the ends, this and then this. And then you can now see the maximum moment, which is at the span 6,127.8 kilonewton-meter. You can see the moment. So this is a very high moment, and it's very nice to, it is what you or one should expect for a long span beam of these 20 meters. Okay, that is fine. So in that course, then say okay. Now coming to the reinforcement arrangement now, you can see the reinforcement that I used 25 millimeter. It's right. So at the top 5T25, although this will be justified based on your design, after your design. For example, if I reduce this down to 4, you can see that it is failing. Okay, it's failing. So I'll increase to what is sufficient. So in this case, 25. I don't want to use lower reinforcement. Now, one of the simple trick, when you have a long span beam, don't use lower diameters of reinforcement. Once your beam span is up to 8 meters, from 8 meters and above, or from 9 meters and above, don't use smaller diameters like 16 diameter, 20. No, even if it's okay, don't use it. Instead, change it to 25 diameter. All right, use lesser diameter of 25 instead of using so many lower diameter of what 16 and then 20. Okay, because as the length is so the what deflection, and you know that since if a bar has a smaller diameter, it will deflect more compared to the one that has bigger diameter. Okay, so I use 25. I don't want to use 32 diameter because of the cost. Because even if you're designing, you also consider the cost too. So consider the cost. So since this 25 is okay, I make my minimum to be 25 for every long span beam from 10 meters, 13 meters, 14 meters and above. Okay, I do this. Now, you can see the bottom reinforcement now. I have 11 T25 on the main bottom reinforcement, and then again I also have 11 again for bottom layer 2, which I'll show you on the reinforcement how this is being placed. Okay, that is fine. This is the link. This link now is called this is the sidebar. That's the web. It's called the sidebar. Because of the depth of 2.4 meters, there should be sidebars. So 10 numbers of sidebars needed. Okay, that is fine. Now this is a link. Because of the high shear force value, one leg of link is no longer sufficient, so it will be doubled link. No more one length, it will be doubled link. So you can see now it has doubled links. If you reduce that to 2, it's going to cause an issue of failure, but you just make it to be 2 because of the doubled link. So I put double link. Most times there's some beams that will require 3, like 3 as a whole, because when you give lesser links, what happens if it's not sufficient? It will burst. It will like burst because of what sway. It will like sway and burst. That's fine. So in that case, then also control your spacing. Always control your spacing, knowing that the maximum spacings for link spacing is 300, but don't always go to that 300. Control yourself between 250 backward, because in Africa and most times people that measure those spacings, you might give them 250, they'll be giving you 270. So if you give them 300, which is the maximum spacing ever, they will be giving you 310, 320, and most times the engineer site like check might maybe having too many beams to check and you just overlook it. Although this kind of beam is very critical, so there must be a critical check, but even in that, still get the principle of don't use the maximum which is 300, try to come back to 200, 250. So that if you give them 200, even if the design was okay to be 300 spacing, and you give them 200 or 250, most times they might give you 270, 230, which is still within the safest zone, right? Not more than the maximum link space. That's fine. So I use my own to be 200. Okay, that's my own culture. Yeah. Then because when you're doing your engineering judgment, you also think of how the people at site will behave, knowing that in Nigeria most times you will design, but they won't call you at. In fact, in Africa as a whole, you are an engineer that did the design, but they won't call you for the construction. They'll go and pick up their uncle, which is not even engineering inclined, but because they've been building house for like many years, they'll call him. So you understand? So those things you also consider those kind of issues, because even if it happens, the first thing they will call is the engineer. Even if you are going to win the case at the court using your own design report and everything, you will win the case. But what they will know at the public that this engineer doesn't know what he's doing, and that has dent your image. That's fine. So you have to make sure you do your engineering judgment based on these things. Okay, that is fine. So in that case, then this other one that is showing ready, I've already explained here that this is just the spacing between the reinforcement where the concrete to pass through. So as long as the value here is more than 20, you are safe. Okay, that is safe, because the maximum aggregate size, that's chipping, like stone size for casting, is 20 millimeter. So what it means is that since this value is more than 20, it is okay, it is safe. I can see the L/D is 8 against 10 point something. It's fine, it's okay, it's not failing, that's fine. So in that case now, you can then say, okay, let's now go diving into the detailing aspect. Okay, that is fine. So the same principle I applied for this beam, I also applied for the other 20 meter beam here too. Okay, so they have the same principle because they have the same span, the same principle. So I also applied for here too. So coming back now to the structural detailing here, I'll first of all zoom in this place where we have the detailed drawing here. So you can see the 20 meter beam here, which you can see here. You can see that 600 by what? By 200. Yeah, correct. Let's now go back to where I said for the support. Yes, I say I will explain that too. Yeah, so back to here now. You can see that I used shear wall instead of column for the supports. Now, what was the reason why I have to decide to use shear wall as a support? I can see that every other beams are carried by columns, which here too would have carried by columns. But the reason why I use shear wall for the supports of this long span beam here is because generally, in terms of when you're designing, you don't look out for only for the aesthetics, you also look out for the system. When I mean system, I mean the framing system. So in general, an ROC wall is more stiffer compared to column. So when you're designing for a bogus structure or a capacity design, so in this case now, these two beams are called capacity design because of their longer spans. Capacity designs are like high-rise buildings that will resist earthquake, buildings that will resist high wind effect like hurricanes. Doing that kind of designs are capacity designs. Then also long span beams that are unimaginable to do. So those are classified as what? Capacity design. So when you're doing that, you should consider also your framing should come into play. So knowing that you can use vertical members can either be column or can either be an ROC, that's a reinforced wall. So in that case, two of these, one has more strength than the other. And what is that? ROC wall is more stiffer than a reinforced concrete column. That is why you see in all high-rise buildings for buildings that they want to use to resist earthquake, vertical members are always preferred to use ROC wall other than using columns, because ROC wall is more stiffer and resists more earthquake than columns. So the same way here, I did choose to use this because of the high moment coming from this beam. We are rating that over 6,000 moments, okay, kilonewton per square meter coming here, right? Which is so that's a very high moment coming to the ends. So at that point, using the column, it will make your columns be even if the column will work, but they will be bigger size. And when column begin to extend more than 1 meter in length, it begins to behave like a wall. So instead of that, because that's how it's going to behave, instead of that, why not convert or change to a reinforced concrete wall? Because using the column for this kind of thing will make your column to be bigger, either in length or in width. And so in that case, since ROC wall resists more load compared to column, I have to use ROC wall because this is a capacity design. That is fine. So that's why I have to make that judgment of using an ROC wall, which is and shows the size that is sufficient to carry the load enough. Okay, that is fine. So in that case now, that takes us back now to our detailing again. That's fine. Okay, so back to here now again. You can now see it here. These are the beams. Can you see that? So this is the beam which you can see here. This is the 20-meter beam, and you can see the section size there. So this is the beam spanning from column to column, and then supporting or carrying the other beams here. So again, you can also see that one here. But let's now move on to the structural detailing for this beam section. So this is the slab within that area. Then let's go to the beam. So this is the two beam, this is the first one and this is the second one, beam 58 and beam 57. Can you see that? Now you can also see the reinforcement here. You can see the first one 6Y25, and then the other two 625. Yeah, you can. But what you saw was 5, right? Because when I did the main design, I used 6 instead of 5. Yeah, and I had my reason for that. For using 6 instead of 5. Then at the bottom, which you can see here, you can see the bottom here 1125, B1 and B2. So you can see the B2. So you can see the B2 here. This is you can see the B2. This is the same thing that we saw 1125. Can you see that? And then for the sidebars, you can see that for the sidebars, you can see 2 times. That is on both faces. You have 10 to 16 on this face of the beam and the other face of the beam. Correct? That's fine. Then you can also see now this is the top and this is the slab. This is showing you the slab line of 150, and then this is the beams that we are coming to connect on that on these beams. So these are the like the trace plan. So the top bar is now knowing that this is a long span beam of 20 meters and the maximum length of our reinforcement was 12 meters. That's what you can see in the market. So the next thing that will face that you will face is how to lap your reinforcement, lapping. And the best way of lapping is to stagger your reinforcements. Always stagger your reinforcement in different areas. Okay, that is fine. So how do you stagger your reinforcement knowing that the length is more than when the length of the beam is 20 meters and more than 12 meters? So you must not lap your top reinforcement and your bottom reinforcement at the same location, else they will create a weak joint on the lapping. Most times those your lap might fail. And knowing that we have 6 numbers of this, all right, and this is where we are lapping it, but make sure that you're not lapping all the 6 at the same spot. So knowing that we have like 6, let me assume that this is 6 now, but it's 4 showing, right? And you're going to lap here, lap here, lap here, lap here, lap here, and lap here. Don't lap all of them at the same spots. So if you lap one here, you have to give a space, let me say forward, either by 3 meter or 4 meter, and then lap the next one at the front. Do you get? Again, the down that is coming again, because you have 6 numbers now. So the first one here, lap it at 2 meters or 3 meters, based on the code standard, you like see that on the code. Then come again here, this one now, lap it forward, maybe backward. This one, lap it at the center. So it is called what? Staggered lapping. You have to stagger the lappings, okay? So the same thing now, where you lap the top should be different from where you lap the bottom. They should not be the same, so that there won't be any weak point created. Okay? That is fine. So that's for the lapping principle. I can see that in my own case, I can see where the top was lapped. You can see where the bottom was lapped. It is not at the same point, like the same spot like this. Okay, correct. So you lap them staggeredly. Okay, and even that staggeredly on that same top, lap it different, because you have 6 number of what 25 at the top. Lap them differently and different location. And also for the bottom too, you have 11 numbers. Lap them differently. You can lap 2 the same place. The next 2 is different place. So stagger it. Then for the connection between the beam and the column, all right, you have to provide enough what development length. The initial or the 𝕼𝕚𝕚𝕡 calculation for the length, which is this length here, that is entering from the beam into the shear wall or the RC wall or the column, maybe in your own case column or something, should be, the 𝕼𝕚𝕚 is 50 times d. That's 50 times the diameter of what of the bar. So in this case now, my own is 25, right? So 50 times 25. That gives me what 1,000 minimum lapping. That's what I meant to take. Now, if you look at my own, if I put my hand here and put your eyes there, I have 2,200. But this value is actually this beam was scaled by 2. So what is here is around 1,200. Because if I measure this now, you can see that it is giving me what? It's giving me 4,800. So it is scaled by times 2. So but our beam depth is what 2,400. Okay, right? So you can see that. So any value that I get here, you just divide it by 2. That's the actual height. Okay, so in this my lapping length now, you can, if I put my hand here, this is where the lap stuff. So if I put here, it will show me, you can see that 2.23 something. So what I use as my lapping length is 1.1. okay, that's what was sufficient in most cases. In most designs, you can even go deeper into the wall just to create enough enough lapping length with the column reinforcement. So with the shear wall reinforcement or column reinforcement, that's fine. So you can see now how this is being done. I can see the section here. Let me show you the section now. So this is the section which you can see the top of the beam here is 6T25. Can you see that? And then this is the slab of 150. This is the side bar which is giving us, can you see that? T25. This is the bar mark. This 101 is the bar mark, not the number. It's the bar mark. Then you then come here now. You then come here. You can see here too. This is 2 times T25, yeah, because it has double links. You can see that double link is there. Then my main focus now is the bottom part. You can see that this 11 T25 first layer and second layer. This is how it is. So what is required is 22 numbers at the bottom. But we need to do a step 1 up as the layer 2. So this is how it is being placed, even at site. They first of all place this 11. Now put a spacer bar. This spacer bar must be the same diameter. That's T25 in this case. 25 that they will cut before they now place this other 11 at the top, this other one at the top. Now note, these values is not a custom value. This was based on my design. In your own case, it can be lower or it can be higher. So note, this is not a custom value. Okay, that is fine. And these depths are not custom depths for every 20 meter beam. Note that. So this is based on my design, loading and everything, and my and the span. Okay, that is fine. So you can now see how this is being designed for. Okay, see you guys on the next video. Now, if this video finds you well, consider subscribing. And if you are an old subscriber or a new subscriber to Ekidel and you want to learn more, consider enrolling for the membership, which we have a detailed videos there compared to the video that we post online. We take our time to explain more there because we have enough time. Understand? On the main public video, we try to not to be too long because of the length of the video. But in that place, since you're paying, you watch. So you can choose your level, starting from students, graduate trainee, graduate students, and then professional engineers. You will see all the levels there. Choose the level. Each of the level comes with the level of video that so choose your right level. Okay, that is fine. Then note that all our oil and gas videos that we are entering by next month, 1st of September, we'll start posting oil and gas video. It will be strictly on the membership. So it is best time not to go and choose a slot, because when we start posting, the price might increase. But if you already choose a slot there, the same price that you're seeing now is the same price that you'll be paying just to watch the video. But if you join after we have done posting, the price might change. Okay, that is fine. And if you want to get an in-depth training, one-on-one training, you can enroll for our Ekidel mentorship training, which is the highest of all. Okay, that is to build the confidence. You will learn more and more. Okay, that is fine. So if this is fine, please consider subscribing and also give this video a thumbs up. See you on our next video, and then bye for now.